So welcome for the second lecture about low-dimensional attractors on hippocampal representations. So I'm going to talk today about data-driven and machine learning-inspired models. So yesterday's lecture was about abstract models of continuous attractors for multiple maps, and what I would like to do is actually today is to divide my lecture into two parts. One is how we can compare the models I explained yesterday, I presented yesterday, to recordings of the activity of behaving animals in situations where multiple attractors can be evoked depending on the contextual information. And secondly, I'd like to, let's say, go away from recordings or experiments and try to think about what could be a minimal model for establishing spatial maps from sensory information. And by sensory, I mean external and internal sensory information. So this second part will be more related to machine learning models. So in fact, what is the necessary information for an animal to navigate? So navigation essentially relies on the estimation, the capability to estimate position. And there are two main sources of information which are used for this purpose. One are called allothetic cues, which may be landmarks, like visual scenes, olfactory, auditory, tactile, sensory inputs, or the Earth's magnetic fields. And the other one are called idiotetic cues, which are, let's say, internal signals coming from the animal body, like related to, such as related to displacement, the speed, the direction of displacement. And they allow for that reckoning, which is also known under the name of path integration. And both sources of information are actually concur to build an internal map of space which can be used for many purposes. So as we said yesterday, the hippocampus is a brain area which is known to be crucial for episodic memories, and this is also the place the area where place sets were discovered by O'Keefe and collaborators in the 70s. And I've already discussed this extensively yesterday. And these place cells are thought to be the basis for the so-called cognitive map, which is at the basis of the representation of space in mammals. So they are crucial for mental exploration, for instance, planning for future navigation, or also for replay during sleep. For instance, when an animal is immobile or an animal is sleeping, then they're on very short time scale, compressed time scale compared to physical motion, then sequences of display sets are replayed, which correspond to possible trajectories in space, preceding a displacement, for instance. Okay, so one question we would be interested in today is actually how place cell activity can be established and updated based on the sensory and self-motion cues, and especially how the two sources of information, depending on how reliable they are, can be used preferentially by the animal during its exploration of space to build this spatial map. Okay, so I'm going to first, in the first part of the lecture, talk about data-driven models based on neural recordings in behaving animals. So the experiments I'm going to consider is an experiment which was done by Karel Jezek and collaborators and published 10 years ago. And so what Karel did is that he actually had some electrode recordings of the activity of hippocampal place cells with a few tens of neurons, which were recording at any time. And an animal was actually located in two different rooms. So these rooms were physically different, but they were identical in terms of dimension. They were about 60 centimeter wide rooms, and they differed only by the presence of slightly different light conditions. On the first room, which I call box A, then some lights were on the roof, and in the second room, box B, we had some lights located on the sides, on the walls of the box. And the two rooms were connected by a corridor which is about 2 meters long. So my drawing is actually wrong here because, as I said, the corridor should be much longer, about 3 times longer than the width of the box. So the animal, the rat, is trained to memorize these two boxes, these two environments, A and B. And we first, what these people did, and Karel and collaborators did, they first recorded reference session where the animal was located in one box or the other. And it could then wander freely from one box to the other. So if you do that, you can see that the same cell, the same place cell, can actually develop different place fields depending on the position of the animal in the two boxes. So here you see one cell and the positions where this cell is maximally active in the two boxes. So the color codes correspond to, so blue correspond to essentially rest activity, which is very low activity, and yellow, orange correspond to very high activity. Okay, so as you see, the difference in light conditions between the two boxes and the fact that the corridor is quite long leads to the phenomenon of remapping I mentioned yesterday. That is, the place field do not occupy the same spot relative to the walls of the two boxes, even if the two boxes are identical. Now, in the second part of the experiments, when these two boxes are learned by the rat, then the rat is placed in a single box, which is managed by with a switch, a light switch, which can instantaneously change the light condition from the one corresponding to box A to the one corresponding to box B. This is why this experiment was called also teleportation, in the sense that the rat was not physically teleported, obviously, but the contextual information related to the two boxes could be changed immediately. So in this test session, the last cue will be suddenly changed from one box to the other. And the question is how the representation, which is the map we discussed yesterday, is going to change when we do this light switch. So the first thing we have to do is to decide which map is actually loaded at any time t during the recording. So the data we have here after spike sorting is can be seen as a raster plot. So here you see this kind of data. So time is the horizontal axis, and the vertical axis has different rows. Each row corresponds to one of the recording neurons. And each time the neuron is active at some time t, then there is a black dot, which is written here. Otherwise, white dot corresponds to a silent neuron. Now, if we consider the population activity, which is the activity of the set of cells in a time bin, and the width of the time bin, the duration is about 125 milliseconds here. That corresponds to the theta rhythm, which is known to be very important in the rodent hippocampus. Then the question is if we see this vector of activity, can we actually decide whether the representation in the hippocampus corresponds to the one of map A or to the one of map B? So how can we decide and answer such a question? Well, we already had all the ingredients necessary to do that, I mean, from the yesterday's lecture. So if we consider neural space in the hippocampus, and we consider three different cells which are recorded, so the green, orange, and blue ones, they may have overlapping receptive fields in environment A, for instance, the green and orange one, while the corresponding receptive fields are far away from each other in environment B. So now, if we look at the activity vector of the 30 or like cells at any time t, then if we see that the orange and green cells are actually firing together, they are actually active in this time in, then it's very likely that the animal is actually evoking the representation corresponding to environment A. In fact, in environment A, it's possible that the two cells are active together, that while it's very unlikely to be the case in environment B. So essentially, what I'm saying here is that the pairwise correlations are fingerprints of the corresponding maps. So what we need to do when we have a vector of activity as the one which is written here on this slide is to be able to score this vector against the pairwise correlation which are characteristic of maps A and B. So how can we score a vector, an n-dimensional vector, against an n by n dimensional matrix of pairwise correlation? So to do that, we will use an inverse approach. So we'll use an effective Ising model, which is actually built from the data and which captures the patterns of pairwise correlation. And this idea was put forward by Schnellman and collaborators in 2006. So the idea we have in a completely different context. They were interested in analyzing retina data. So here what we will do is that we will build two different models. One model for map A, another model for map B, and we will use the reference session to do that. So the idea is to have a function, which in this particular case is a probability, which tells us how likely is a certain vector of activity, S at time t, within the model corresponding to map A or within the model corresponding to map B. And the model we will use is a graphical model, which is also called Ising model in statistical physics, while here there is no translation invariant, no nearest neighbor as in the usual ferromagnetic models. It's just a model where all the possible pairwise interaction exist, Jij, between all pairs of neurons I and J. And also we have local fields here, which depends on the particular neuron we are considering, Hi. And both Hi and Jij, the set of parameters here, do depend on the map A or B we are considering. So what we want to do is actually to find the effective couplings J and the effective inputs H, or effective fields H, as you want to call them, from the data which are, the recording data which are collected in the reference session A or B when the animal is wandering in box A or in box B. So how do we do that? So let me be a little bit more precise about this approach, which is an inference approach, an inverse statistical mechanics approach, if you want. Usually in statistical mechanics, we start from the knowledge of the fields and the couplings, and we derive some values for observables. Here we will do exactly the opposite. We will have observables, which are the mean activities and the pairwise correlation between the cells, and we will infer the coefficient of a Hamiltonian, or if you prefer, of a Gibbs measure, which is written here. So again, so what is going to be the procedure? We start from a raster plot, which corresponds to the activity of the neurons, the different recording neurons as a function of time. And from that, we will compute the mean activity of each cell, so SI, average over the time beans, and the mean pairwise activities, SI, Sj, for all pairs of cells. So if we have n recording neurons, we will have n mean activities and n times n minus 1 over 2 pairwise correlation SI, Sj. So that defines a network of correlation here, and what we would like to do is to find the Ising model with unknown parameters Jij and unknown local field Hi, which is able to reproduce exactly the mean activities and the mean correlations here. So this is why we call this an inverse problem, which is actually a high-dimensional fit of data, if you prefer. Okay, so why are we considering the Ising model and not something else? There could be many models which actually are reproducing the mean 1 and 2 point statistics, the 1 and 2 point statistics. The reason is that the Ising model satisfies the so-called maximum entropy principle, which was advocated by James half a century ago. So the idea is that it is the least constrained distribution of a set of configuration, of neural configuration, with the right 1 and 2 neuron statistics. More precisely, if you define the Shannon entropy as a sum over all possible configuration of minus P of S log of P of S, where P of S is the probability of a configuration S, of a vector of activities S, then the Ising model distribution, which is written on the top of the slide here, is the one which satisfies the constraint that the sum of S of P of S of Si is equal to the value of Si in the data, and sum of S P of S Si Sj is equal to the correlation measurement of the data, which maximizes the entropy here, the Shannon entropy. So it's a least constraint distribution capable of doing that. Yet we have to find the Jij and the Hi, which is not a simple thing, right? If you consider that we have, let's say, a few tens of neurons, like 30 neurons, so there are 30 unknown fields here, and there are 30 times 29 over 2 parameters for the effective couplings here, which have also to be computed. So to do that, we can use many different algorithms, and maybe the simplest algorithm, but maybe not the most efficient, but the one I want to tell you about today, is the so-called Botswana learning machine algorithm. which was put forward by Ackley and collaborators in 1985. So the idea is very simple. The idea is to use massive Monte Carlo simulation. So you can start from random guesses for Gij and Hi. I mean, all these parameters. Maybe all the Gij are equal to 0, for instance, and the Hi are given by the log of the mean activity of each neuron or something like that. And now what we can do is we calculate using Monte Carlo simulation for this particular set of Gij and Hi the correlations and the mean activities within the model. And then we compare our findings to their counterparts in the data. And this is what is shown here. So for each pair of neuron Ij, you will compute the difference between what you find with your Ising model corresponding to these parameters and what should be the target value obtained from the experimental data. So then if the two values here match, the difference is equal to 0, then this is very good, but in general it won't be the case. So if we find that the difference is positive, that means that it's likely that the pairwise interaction between I and j is too large in our model, so we like to decrease it. So we do some kind of gradient descent algorithm where we will simply decrease Jij by some amount which is proportional to the difference here. And we do exactly the same thing. We will find, for instance, that the mean activity in the model is too weak, is too low compared to what it should be in the data. That means that we should probably increase the field Hk, and we will do that by subtracting from Hk something which is proportional to a negative difference here, so that will increase Hk. So A is called the learning rate, and it's a hyperparameter which is adapted to the situation. Okay, and if you repeat that, then we have some guarantee, since this is basically an algorithm which is minimizing the cross entropy here of the data and the model distribution, we have some guarantee that after enough time, then we will reach a solution to the model within some accuracy. So there are many issues about this algorithm I don't want to discuss here in details, like the issue of sampling. We have to be sure that Monte Carlo's estimates are accurate enough. And about convergence, so there could be some flat modes here, even if a function to be minimized is complex. Anyway, so let's assume we can solve this computational problem and we find the Ising models. And we have to do it twice. One from the data corresponding to box A, another time for the data corresponding to box B. So we get two models. And before I show exactly what we can do with the model, let me just show something which I think is interesting, because it will be a reminder of what we said yesterday. If you look at the interaction we find here, for instance, in box A, and that corresponds to one of the data sets which was recorded by Carrère, we can plot Jij here as a function between the distance between the place field centers, between the neuron I and j, in the arena A, in the box A. And you see there is a lot of dispersion, but if we plot the sliding average as a function of the distance, we see that Jij is positive at small distances and becomes negative at large distances. So this is very nice because that corresponds exactly to the ingredient we put in the model I explained yesterday. In particular, this is exactly what the Sovik-Sejnowski model is about. So we find that the data are actually compatible with the abstract model I introduced yesterday. Okay, so once we have the two models, how can we decode the map? Well, what we will do is that for a given vector of activity which corresponds to the activity recorded at time t during the test session, we will compute the log or probability of this vector of activity within model A, so log of P of st given A, and compare to the log of the same vector of activity within model B. And if the difference is positive, we will say, oh, then it's likely that this configuration was actually drawn from model A. If it's negative, we will say just the opposite. And that will be our guess for the map which is loaded in the Hypocampus at time t. So let me show you first that this is actually an efficient and effective way of doing this. So what we can do, we can use the data used in reference session A, but not the one we use for them to draw the model, but the data which we're recording in a different reference session, right? A. So the rat is only in box A. And I can plot here the difference in log likelihoods, in log probabilities between the two models. And you see that it's always positive except at two moments here where the activity is very small. So, and if we do that with data coming from box B, we see exactly the opposite. In fact, if we plot the histograms, we see that the histograms are always negative or positive, depending on whether we consider reference station B or A. And there is a very tiny fraction of the timings in which they overlap. So in this tiny fraction here, we cannot decide whether the animal is in box A or B, but for most timings, we can actually very safely recognize the correct box. So we have very good performance, and I want to insist on the fact here that we do not use at any time the true rat position, which is known because a camera is actually filming the position of a rat. Okay, so now, since we have our map decoder, we can use it and see what is going on when we do a live switch, so this test session I was mentioning before. So what you see here is on the horizontal axis is time, which is expressed in theta cycles. So if you want seconds, you have to divide by 8. And what you see on the vertical axis here, on the top panel, is the difference in log probabilities between the two decoders. Okay, so the vertical bar, red bar here, corresponds to the time at which the live switch was changed from condition B to condition A, which corresponds to this drawing here. So originally, the animal is in the box with live condition corresponding to B, and we see that consistently delta L is always negative, except when in some position of a rat, actually we have no place cells which are active, simply because we have only 30 cells which are active. That does not cover uniformly the whole space, the whole set of position in the box. But it is very consistent with the representation B. Now, what is interesting is what happens right after the live switch. What we see is delta L becomes positive, then negative, positive, negative, and so on, and we see some oscillation. And then after a few seconds, then consistently with the new live condition, the representation is compatible with box A. Okay, so the most interesting phenomena is this kind of instability between a few seconds here, where the representation seems to oscillate or to fluctuate between the one corresponding to box B and box A, while the light condition is actually very much stable and corresponds to box A. So these events were called flickers by Jezek and collaborators, and this flickering event seems to be more frequent right after the light switch and to disappear after a few seconds. So one first question we asked was whether the encoding of the position of the animal was actually, let's say, precise or accurate during these flickering events. So essentially, if I want to summarize it in a few words, after a few seconds, right after the light switch, it seems that the representation, or let's say the map which is used by the animal, is actually changing very abruptly and fluctuating. Does that mean that the information about the position is lost, or does that mean that the animal has two different ways of expressing this position? So this is what we wanted to understand, and in order to do that, we used the position decoding, which was actually introduced a long time ago when people started to look at place cells. The idea is very simple to do that. In the reference session, when you record when the activity of the animal is recorded at the same time as its position, then rate maps, which correspond to the activity of the animal for each cell as a function of its position, can be drawn. That corresponds to the place fields I was mentioning yesterday. So we know what is the average firing rate of neuron I when the rat is in position X, and that we call Fi of X. Now, if I know the activity vector SIT in some time in T for the all neurons I, then I can infer what is the most likely position X, knowing these rate maps here. But of course, I can do that in two ways, because I can use the rate maps corresponding to the map A or to the map B, that is to box A or to box B. So that means that for each activity vector, I can infer two positions. One which would correspond to the position of the animal in box A, and the other one which would correspond to the animal in box B. So if we do that, then we can decode the position of the animal, and this is what I'm doing here. So let's look at the top panels here. As a function of time, which is horizontal axis, you see the position X and Y of the animal. So the orange curves here correspond to the real position, which was taken by the camera on top of the rooms. And the blue one corresponds to the position which is inferred by our decoding algorithm for the position. So what we use here for the red maps is the one corresponding to the external light condition. So before the light switch, which corresponds to the red bar here, you see that there is a very good agreement between the two trajectories, the real one and the inferred one. But right after the light switch, there is a large disagreement. And that is very much compatible with the idea that the representation used by the animal is not the one corresponding to the external light condition in the few seconds right after the light switch. So now if we use first our map decoder, the one I just explained, in order to infer what is the map in each time being, A or B, and then we use the place fields of the red maps corresponding to this decoded map A or B in order to infer the position, we see that the agreement between the inferred position and the real position is now very good. So that means that decoding of position is actually very accurate if we use the map, which can change very quickly, but we use the map which is inferred by our map decoder. So the error is actually very small and close to what we had in the reference session. So if I want to summarize this finding, it means that the rat has actually two different ways of expressing the position, either with the map associated to box A or the map associated to box B. It can choose either, and in fact it does so, and it can change it very quickly on time scale of the order of 100 milliseconds, which is the theta rhythm. But even if it uses A or B, the position encoding is always very precise. It's a little bit like, you know, I'm speaking here in English, but I could alternate between English and another language. So for instance, French, which is my native language. But I could actually express some, some sentence with a very precise meaning and alternating between the two languages without losing the meaning of this sentence. So the way I express this meaning would change over time, but the value of what I'm saying, the content would be still constant and would be precise at any time. So it seems here that the language is changing, but the content, which is the value of a position, is actually precise at any time. So if I want to summarize what we have found, it seems that we have two attractors here, if I use the vocabulary we had yesterday. These two attractors correspond to box A and box B, and are expressed in the same network, the hippocampal network of the rat. Now, as the rat is moving, the collective coordinate along the first attractor, which corresponds to box A, for instance, is changing. At some point, after the light switch, for instance, there are some spontaneous jump towards the other attractor, which corresponds to the one of map B. Then the rat is moving in map B, and its position along this attractor is updated according to its motion in the box. And then there is another change and jump to the other attractor and so on. The point is that when the attractor is changing and the jump in the activity is seen in the data, then the position of the rat is always very precise. That means the activity vectors is jumping from this one here to that one here, and they correspond precisely to the activity vectors that code for the real position x of the animal. So the activity vector is not jumping from this position, from this one here to any random fixed point along this attractor. No, it's jumping to the activity vector, which corresponds to the exact same position x here. So we need two things here if we want to model this observed behavior. First, we need a model which is able to jump from one continuous attractor to another one. And that we have already done yesterday. But what we need is another ingredient that we didn't have yesterday, which is we need to be able to jump between configurations corresponding to the exact same physical position. And that was not the case yesterday. So I just want to make a very brief reminder of yesterday's lecture. Remember the model we used, which was introduced by Samsonovich and McNaughton, where we have actually a prescription about the synaptic interaction matrices, which correspond to some matrices I'm building from the relative distances, the relative position between the place fields of the different place cells in the different environments. So as I said yesterday, there is a phase diagram which tells me that if the number of attractors I want to memorize in the network is not too large, and the neural noise is not too large, then I can have nice bump attractors here, even if there are some issues about the spatial resolution I mentioned yesterday. But these issues are not too large and not too problematic if the number of attractors is actually small, and here we are considering 2 attractors only. So something which is interesting I did not mention here yesterday is how we can actually jump from one attractor to another, irrespectively of the position which are encoded by the activity vectors on the 2 attractors. So what we have seen with Sophie Rosa some years ago is that there are 2 mechanisms for this jumping, depending on where we are in the phase diagram. So the first mechanism is something I would call evaporation condensation, in the language of statistical physics I introduced yesterday. The idea is that on the way between the first attractor and the second attractor, actually the activity is actually not corresponding to any point on any of the 2 attractors. So it's something completely different, which is like going from one ferromagnetic state here to another ferromagnetic state through the paramagnetic phase. Yeah. And that happens at sufficiently high temperature or sufficiently high neural noise here. Or loading, or load here, that is sufficiently large number of attractors, even if we don't want to leave this ferromagnetic phase here. If we are at low temperature, this evaporation condensation mechanism doesn't take place. And transitions between one attractor to the other one takes place through some mixed state, where for some transient period of time, then some kind of mixed state, which is half on an attractor and half of the other attractor, is actually taking place. And this is possible only at some specific position of the animal, where just by chance, the 2 maps are actually very similar. It could be that at some position X in box A, maybe a sequence of 3 or 4 place cells are actually activated because they have actually overlapping fields. And the same sequence of 4 place cells are actually activated at a completely different position in the other map B. So these are some kind of gates where actually the 2 attractors can communicate and the activity can jump from one attractor to the other one. Some kind of wormholes, if you want to use a trendy vocabulary. So managed with these possible scenarios for jumping from one attractor to the other one, we have now to understand how it's possible to go from one position coding from the same for the location X to the activity vector corresponding to the same position onto the attractor, the other attractor. So in order to do that, we need some ingredients which correspond to inputs, sensory inputs. So there are different kinds of sensory inputs which are very important here. And the same kind of, the first kind is our visual inputs. So visual inputs have been characterized in many different experiments, and one I would like to mention here are experiments by O'Keefe and collaborators in virtual reality. So in these experiments, a rat is actually has its head fixed and can move on a rolling ball. And depending on the number of turns of this ball, then a movie is actually run here on this very large screen. So the animal is actually moving in this virtual environment depending on the motion of its legs. So if you do that, and maybe the animal is moving on a 1D track, then what you will see is that place cells appear, and the activity of these place cells can be measured, and you see, for instance, look at the top line here, you see nice place fields corresponding at different positions along the track. Now, what can be done is actually some kind of decoupling between the way the movie is presented to the animal and the motion of the legs. So, for instance, the movie can be played at a velocity which is 1/2 of the rotation of the ball, or maybe twice. And what you see is that some place fields actually don't move when there is this decoupling, and other place fields completely disappear. So clearly that means that some place cells are actually related to the motion of the legs. So they have a place field which correspond to the position on the environment, which correspond to the number of turns of the balls. So the coordinate is related to the motion of the animal, and other place fields are actually related to the position along the movie. So they are really anchored by the visual stimulus which is received by the animal. So about 25% of place cell in this experiment seems to be driven by visual inputs only. So the other source of the different source of information that the animal can dispose of are coming from path integration. So path integration is actually the integration of the motion of the animal. So the exact mechanism supporting path integration is still not totally understood, but a lot of information has been obtained over the past year through different experiments. So I just want to mention some of them here on this slide. So it is known that if some lesion in the hippocampus and also the brain areas which are very close to the hippocampus, in particular the medial and terminal cortex, which supports grid cells, can impair PI performance, path integration performance. It is also known that inhibition of NMDA receptors in the medial and terminal cortex impair grid cells, but to a much less extent other space-related cells such as border, head direction, speed cells, and so on. And it has this inhibition has some effect on the path integration performance. So it's from this kind of data. I mean, it has been hypothesized that actually the medial and terminal cortex and the grid cell networks could be a support. It's a candidate for support of the path integration system. So the path integration system is actually allowing the animal to integrate its own motion in order to update its position over time without any other kind of sensory, like visual or olfactory information. So what we have supposed in the model is that the two sources of inputs were actually present. And we have supposed that external inputs were actually sending some information on place cells, depending on the position of the animals in environment A or B. And also, inputs were also related to the path integrator, depending on the position of the animal. So, so here you see what is going on. Sorry. So you see what is going on in the model prior to the change of light conditions. So prior to the light switch, is that the two sources of information, the path integration coming from the integration of the motion of the animal, and the vision inputs actually activate the same cells in the representation, let's say, of map A, if we are in position A. Then, after the light switch, the visual inputs will actually correspond to the inputs you would expect in map B if we change the switch from A to B, while the path integrator has some inertia, which is related to the fact that the animal is still moving and has some, let's say, memory of the past environment, which was map A, corresponding to map A. So what is going on is that the visual input will now point towards cells which correspond to the position of the animal in environment B, while the path integrator is still pointing and trying to switch on the cells which correspond to the position in the animal in map A. And these are different cells. And this conflict between the two sources of input will take place for some seconds until the path integrator is actually reset, and the adequacy between the path integrator and the visual inputs will be restored, and they all point towards the same cells corresponding to the position of the animal in map B. So we have modeled these two sources of input on top of the network of interaction I had described yesterday in order to have two different attractors corresponding to two maps. This was done in this paper, and I want to show you the simulation. So this is exactly the same kind of representation I had yesterday with the same vector of activity of the neurons, which is represented in two different ways, and we put a dot for the cells which are active at the position of the center of the place fields in the two environments. And we simulate here the change of light with this conflict between the two sources of inputs, which will take place here. Okay, so you see when the conflict is taking place between the two sources of input, and if the two sources of inputs have comparable strengths, then we see some kind of alternation between the two environments until through some resetting mechanism, the path integrator will actually be in agreement with the other source of information, which are visual inputs. So let me play this again so that you see it. So you see up to here, we have a single bump in environment A on the left. And then after the light switch, then we'll see that depending on the time, then we'll have an alternance between these two representations. Here it's in A, and then we will jump into map B. Here you see a dense bump in map B, and then A and B again, and finally there will be a resetting which favors map B. So this is in very good quantitative agreement, which was seen in the experiment I've shown before. So actually the model is making two different kind of predictions. We can also check very accurately on the data. The first one is that we predict that the decay in the flickering frequency we have seen in the experiment is actually a conjunction of two different factors. So here you see the fraction of time the network is actually in the map opposed to the external light condition. So this is 0 before the light switch, or very small. It's large right after the light switch, and it's decaying exponentially over a few seconds. But we explain this as a superimposition of two mechanisms. One is we have a path integrator, which actually can be in a conflict or in a coherent mode. So that means it points towards cells which are different from the one activated by the visual inputs, or they are the same. And on top of that, when we are in a conflict mode, then we have a time-independent probability of flickering, of conflict between, we can be in map A or map B independently of time, on the time elapsed after the light switch. And in fact, this is exactly predicted by the model, and in very good agreement with what we see in the data. So we really think that there is a two-player mechanism taking place in the experiment. One is the fact that there is a conflict between two sources of information, and as long as the conflict is on, then the two representations are essentially equally likely, the one corresponding to the path integrator and the one corresponding to the visual inputs, and we see this jump from one representation to the other. And the conflicts will stop, and the mechanism for actually the resetting of this conflict, the resetting of path integrator, which puts an end to the conflict, seems to be a very simple Markovian mechanism, which has an exponential decay over time. The second prediction of the model is that during the conflict period, the representation, let's say the activity vector, is actually somewhat of kind of superimposition of map A on map B, and this is very easily seen here. So let me just be precise here. So either map A or map B is loaded at any time in the hippocampal network. But when map A is activated, so for instance in this situation, some neurons which correspond to the position of the animal in map B are excited by the other source of input. And this is the same thing here. So that means we don't have a pure representation as we would have before or long after the light switch, but we have some kind of a little bit disturbed representation where some neurons which do not correspond to the map loaded, to the loaded map, are activated but point to the right position in the other map. So we have some kind of slightly mixed nature of a representation in the model, and we see that also in the experiment. In particular, we see that here, that is, if we look at this conflict period here, just a few seconds after the light switch, then if we decode the position of the animal with the wrong map, before the light switch here or or a long time after the light switch here, we see that the error on the position is about 30 centimeters. But the size of the box is 60 centimeters wide, which means essentially the error is half the size of the box, which is just a random guess of the position. So total error here. But if we do exactly this, so we use the wrong map, not the one predicted by our map decoder, to predict the position, we see that during this conflict period here, the error is smaller, and it's substantially smaller. It's still very large, but it's 5 centimeters smaller. That is, there is a little bit of information in the activity configuration we can actually use or exploit even if we use the wrong map. And this corresponds to these few neurons which are activated by the inputs. Okay, so I will stop here in this activity on these data-driven models, but I just want to make clear the point that the abstract models I have introduced yesterday can be confronted with some success to what is going on really in recordings obtained during experimental behavior of the animals. So I would like to switch now to the second part of the lecture, which is going to be more abstract, since I want to now think irrespectively of any kind of model like the one we introduced yesterday and any kind of data as the one I analyzed today, about what could be the minimal model capable of establishing some spatial maps from sensory information. So now I don't really care about neuroscience constraints anymore. I just want to build some kind of minimal model which is able to do navigation, or actually to represent space in a meaningful way. So I will consider some agent which is navigating in a 2D environment, and there are some objects which are present in this environment, just to make the environment not uniform. And the animal, or the virtual animal, the agent, will have access to 2 sources of information, as we believe is the case in reality. Visual, so like allothetic cue, so it depends on the position, and proprioceptive information, internal information, which means each time the animal is moving by some vector A in the environment, then an approximate copy of the displacement of the motor action A is going to be actually available to the animal. It won't be a perfect source of information. It will be noisy, but that is a source of information which can be used to update its position. At the same time, also, the visual information is not always available, for instance, in the dark, or in specific situation. It could be that the image that the animal can actually use is completely distorted, and so the animal will have to make some choice between which source of information it wants to use. So there are many questions we can ask, and especially 2 questions are very important here. How can we teach a recurrent neural net to support a map based on this external and internal information? I mean the visual information and the copy of the motor action. And how can we represent the updated, how can this representation can be updated along the low D-dimensional attractor from the displacement input? And this is very much related to the issue of path integration I mentioned before. So I will be interested in the second aspect here, but before I will do that, I will look at the third version, which is how a recurrent neural network is actually able to integrate information. So let me forget a little bit about spatial maps and try to solve a little bit the problem which is useful, which is interesting, which is how a signal can be integrated by neural nets. And you will see that the kind of neural representation we get is actually relevant for what we will see when we go back to the spatial problem. So, so I will ask the following question: how can a neural networks be able to integrate a signal, or let's say multiple signals? So imagine you have multiple input channels, 1 up to D channels here, with some inputs which depends on time, x1 of t, xd of t, where t is the time. This input can be, for instance, +1, -1, 0, whatever, as a function of time. And we have a network of neurons, and the neurons I will call H. So H is a vector, it's an n-dimensional vector of the states of the neurons, and they are connected through some W matrix, the weight matrix W. And what I'm going to do is that I will update the state of my network like in the following way. So HT, so the neural states, will be equal to some nonlinear function of H at time t minus 1 multiplied by the weight matrix plus the inputs. And so my network will be a recurrent network whose state will change over time. And I will have a reader part of the network with output neurons, which will read the state of the recurrent network and will output here the y1 up to yd, so d output channels as a function of time. And I would like to perform the task of integration. That means the output neurons should be equal to the integral of the input neurons x. So this problem has been actually considered by many people over the last decades. And they were especially interesting in it's very easy actually to do such integration when you use linear networks. So if f here, which is updated here, is just the identity, so you have f of x is equal to x, so you have a linear network, and it's easy actually to implement an integrator by simply aligning some, by building specifically some W should be of low rank, and essentially you should match the top eigenvalue of W with 1 to do a perfect integrator, or if you want an integrator with some loss, gamma here, gamma smaller than 1, then the top eigenvalue of this W matrix should be equal to gamma. And that does exactly the integration task you can be interested in. If you have D channels you would like to integrate, then it's easy to have D different eigenvectors corresponding to the D channels, and they will not interfere because they will correspond to orthogonal modes. And so you can have exactly D integrators in the same network. Now the question is, how do we do that when we have a non-linear function f here, which is a much more realistic and interesting case. So again, this is the definition of the model, where you see the update rules for the dynamics of the recurrent network. You see the decoders here, the decoder neurons, which actually compute the projection of the state of the activity at time t onto some reading vector here for each channel C. And the target we want to achieve is that the input for each channel will be some plus or minus 1 or 0 over time, and we want to integrate this possibly with some decay gamma, which is some number smaller than 1 but close to 1 in practice. So we train the network in such a way that the loss function, which is the difference between the target integral here and the value of integral which is realized by the decoder neurons, is actually very small, and that should be true for all the channels on all the times. So we want to minimize this over the W matrix, and we do that using gradient descent over W using stochastic gradient descent or some solver like Adam. So as I told you, this is very easy to do with the linear network. So let me go to the interesting case of nonlinear networks. So for instance, rectified linear units activation, where f of x is the maximum of x and 0. So when we do numerical experiments, what we see with a single integral, so a single input channel, we see very clearly the emergence of two subpopulations, which are active only depending on the sign of the integral. So one subpopulation is actually active only when the integral is positive, and the other population is active only when the integral is negative. And the activity value of each neuron within each population is proportional to the integral. So if I want to be more precise, what we see is exactly this. Here you see the activity of the two populations, the red and the blue population. So it may be that actually the whole network is not composed of the two subpopulations only. There might be some neurons which are never active, but these two populations actually do exist. And if you look at the value of the integral here, which is y of t, the target integral here, then it coincides with the value here of the red population from the plus population here when the integral is positive, and it's exactly minus the activity of the blue population when the integral is negative. So how does that work more precisely? You see that h of t, which is the activity state of the network, is equal to the value of the integral when it's positive. So here this bracket plus means exactly this function here. So it's equal to the argument here, which is the integral when the integral is positive. It's equal to 0 when it's negative, times some vector here, which is independent of time. And this vector here depends on the neuron. It defines actually some coefficients of participation of each neuron to each subpopulation. So it will be positive for the neurons in the plus population, will be 0 for the neurons in the minus population. And we have exactly the same thing for the neurons in the minus population, where the argument of the bracket function is minus the integral. So that means that our network is made of two subpopulations which are active whether the integral is positive or whether it's negative. So it's a little bit of a partition of a network of a neural population. It's actually, you get a much simpler representation if you look at the currents incoming onto the neurons. So the current is defined here not as the state of the neuron, but the argument of this function, before we take the nonlinearity. So the current here is actually a linear function of the integral with some vector L here, so it's proportional to the value of the integral. And depending on whether the sign of L, depending on the sign of L and the sign of the integral here, then the argument of function will be positive and negative, and the neuron, corresponding neuron will take part to one of the two subpopulations. So we see that there is a one-dimensional current line which define two subpopulations. So what happens when now we have to integrate two-dimensional or higher dimensional signal? And this is the question which is important, because when the animal is moving in space, it has to maintain or update its position. And the position in generic environment is not a one-dimensional coordinates. It's a multi-dimensional, let's say 2 or 3-dimensional position. So we have to integrate coordinates along several directions at the same time in a single network. So what they find is that this linear dependence of the currents onto the 2 or 3 integrals, or the d integrals we want to compute, is still maintained to some very good approximation, and this is the outcome of numerical experiments. But now each neuron, actually, when you look at its activity over time, here depends on the, in a non-trivial way, on the 2 integrals. So here, so maybe I will switch to this plot where this is very clearly seen. So here you see, for instance, for one particular neuron in this very large recurrent network, its activity as a function of the 2 integrals, y1 and y2, we would like to be able to decode. So you see that there is a line here and which separates, let's say, a zero activity region from a non-zero activity region here. And the activity of the neurons is actually not a function of y1 and y2 only, but it's a function of both integrals here. So we have a result which is very strongly reminiscent of the concept of mixed selectivity in computational neuroscience, which was put forward very strongly in a well-known paper by Rigotti and collaborators 8 years ago, which means that if you look at a multi-dimensional sensory information, and if you look at the activity of neurons, which depends on multi-dimensional sensory information, then the activity is actually dependent on all these channels, information channels. It's very rare that the activity of neurons will depend only on one of them. It could be actually if this angle theta here, which is this decision line here, is actually equal to 0 or to pi over 2. But if we look at the distribution of this angle theta over our population, in numerical experiments, we see that it's essentially flat and uniform over all angles here. So most of the neurons will actually have an activity which depends on both integrals. Only a few neurons will have an activity which depends only on the integral of one channel or of the other channel here, corresponding to angle 0 or pi over 2. Okay, so we see the representation of the integral here in this network, which is the only purpose of is actually integration, depends in a non-trivial way of the 2 integrals to be maintained or to be computed from the input. So now we can turn back to the original problem we were interested in, which is both the integration of the motion of the animal, but also the use of the visual external information. So how can a network do both things, integration and also exploitation of the external information? So in our model, the animal is actually seeing the environment, which is made of different objects, with a retina. So the retina here is a set of 64 by 64 captures with 3 color channels. And as the animal is moving in the environment, the position of its retina is moving with the animal, obviously. So it will see the same set of objects, but with different relative intensities depending on how they are centered with respect to the retina. So each channel will send a signal that depends on the distance between the center of the retina, which is the position of the animal, and the object, if any object is present, obviously. And this is very realistic, and it is reminiscent of what you would expect from retinal ganglion cells, which measure the local contrast here. So the input, which is the image, is just a vector 64 by 64 times 3, because we have 3 colors, a vector here, and it depends on the position of the animal. Now, as the animal is moving, then this retina, which is represented by this box here, is moving, and depending on the action, it will see the world and the set of objects in a different way. So what we will do is build first a minimal model, which has 2 requirements. The forward requirement. If we have an image at time t, I of t, which is provided by the retina, and we do some motor action A at time t, then the model should be able to predict the new image at time t plus 1. That's the forward prediction requirement. We have also backward requirement. If we have the image at time t and the new image at time t plus 1 after some action has been done, then we would like the animal to be able to predict the action which was done, at. So here is actually what we do. We train very simple feed-forward neural networks with 2 layers with adjustable weights to do actually these two, to implement these 2 computation modules, the forward requirement and the backward requirement. So the forward again is that given an action, a motor action, a displacement, and the representation of some image at time t, what is the new representation we would expect for the image at time t plus 1? So that's a kind of prediction module about what we expect the animal to see at time t plus 1. And the backward one is, given the 2 representation of the images seen at time t and t plus 1, what is the action which correspond to these changes in what we've seen from the world. And we train these 2 networks to do that. And they are just very simple feed-forward networks, and we see actually that it's possible to do that with good accuracy, with simple architectures. We just have some convolutional modules which take the images, and then a full dense network which is predicting for the forward and the backward models what is expected. And we see that essentially what we have representation, neural representation, which depends on the presence of the forward and backward modules. So for instance, without the forward model, only with the backward, we are able actually to reach a good loss, a good value of a loss for the motor action. But the representation of the neurons, and you see 4 different neurons here, for an environment corresponding to 9 different rooms here, which is a snake path here, and they are not so smooth. While if we impose also that the forward model loss is actually very small, we get nice representation which are quite smooth of the space. You see the values of the activity of the neurons depends very smoothly, continuously on the position of the animal in space. Okay, so we have these very simple elementary modules which compute what is the next image expected or what is the action expected from 2 images. And now we'd like to do something more elaborate. We'd like to do path integration. So we want a network which is able, if we start from some position at time t equals 0, to incorporate all the external information and also to integrate its position from the noisy copy of its motor action to produce the total displacement at any time. And it can be a large displacement in space. So we will do that by integrating the 2 sources of information, and the network has also to decide which kind of sources of information is actually important. So if we have noise in the afferent copy of a motor action, and we have noise in the images, then we should not weight the 2 sources of information in the same way independently of time. So the network has a gating mechanism which is able to put more importance on one source of information or the other as a function of time. So if we do that, then we'll see that actually the network is able to learn how the gating mechanism should act as a function of time. And in particular, it learns how to use sources of visual information when they are reliable. So for instance, if most of the time we don't present any image to the network will put 0 weight for the image. And when an image is presented, it will actually use this information to reset the path integrator. So by using only the noisy copy of the motor action, the network will have an error which increases as the square root of time, which is what you would expect exactly for diffusion. But when the images are present, then you can use these reliable sources of information to actually update exactly its position and the representation of a position. So you see that here on this trajectory of the animal in the snake pass environment. So the color here correspond to time. So blue corresponds to initial times, and red here to the last position of the animal. So this is a forward and back pass standing here. So the true position of animals are the plus crosses, and the estimated position correspond to the star. And each time an image is presented, then you have a small circle here. So you see that there is a divergence between, a small discrepancy between the estimated and the true position of the animal. And when an image is presented, and that corresponds to this circle here, then of course you get exactly a right resetting at the right position, because the image here is totally reliable. So you see that the network is able to implement here a good mechanism which uses reliable external information to do the resetting. Now, what is important also is that visual information only is not sufficient, because you could be in a situation where visual stimuli are ambiguous. And we do that here in the bigger environments, where these two external rooms here, the two rooms onto the extremities, are actually managed with exactly the same object. They have exactly the same objects, and the two rooms which can communicate with this one have exactly the same set of objects too. That in the animal where it's here cannot rely only on visual information, because otherwise it could not make the distinction between the two rooms. And only with the use of the path integration and representation that really depend on space, not only on visual information, then the two rooms can be actually disambiguated. And you see that here, with the path integral information or mechanism, then the network is able to have representation, and that corresponds to 3 different neurons here, whose activity really depends on the position in a continuous and very nice way. But without this path integration mechanism, then there is a total ambiguity and confusion between these two rooms here, which have exactly the same representation, and which is completely wrong. Okay. So I will stop here, and I will take questions. So what I wanted to show you in the last part was the minimal model, allowing an agent to build a coherent representation of space from visual and self-motion inputs. This is based on the combination which is absolutely needed to disambiguate similar visual scenes far away from each other and to reach good positional accuracy. And we see that the neural representation which were obtained, and you see that here, are very similar to what you would expect from a recurrent network doing pure neural integration. One aspect which is important is that the kind of representation we get here is very different from what we would expect from place cells. We get a continuous representation here. We don't get set of space of location where the cell is very active and it's not active anywhere else. So this is quite interesting result. That means that completely different kind of representation from what is observed in experiment is possible in artificial networks. And of course that raises the question of why maybe the objective functions which are realized in animals are very different from the one I've shown here. But I think it makes the point that there is a large diversity of neural representation which can achieve this minimal spatial navigation task. So I will stop here and take your questions.